All right, welcome back to part two. So today, our goal is simple. We're going to nail the continuous spectrum. So first, I'm going to describe the setup. So we're going to be dealing with measure-preserving dynamical systems that have a invertibility property, and this will induce a unitary Koopman operator. And I'm going to walk through several sort of algorithms to MP-EDMD, which is a measure-preserving version of EDMD, where you constrain the approximations to be unitary. We'll talk about how it approximates spectral measures, and then move into Riggs DMD, where you see something called generalized eigenfunctions, which give you sort of like the Koopman modes, essentially for Koopman operators for continuous spectra. Okay, so the setup. So remember, we have this Koopman operator, and for the time being, we're acting on this L2 space, okay, of observables. Okay, so you have G at time n is given by n-fold applications of the Koopman operator evaluated first point. And what I'm going to do is assume that this system is measure preserving. So this F preserves the measure omega. This holds if and only if the Koopman operator is in isometry, if and only if k star k is equal to I. And this implies the spectrum is a subset of the disk. Now, if k is invertible, it's a subset of the circle, and the Koopman operator is unity. If k is not invertible, then the spectrum is the whole disk. So what you can do is you can either assume that F is invertible in a measure theoretic sense. That will enforce that the Koopman operator is also invertible, and then you get a unitary Koopman operator. Or you can actually do something called, you can take something called the Wald decomposition of an isometry, and this gives you a unitary extension. So, and in fact, the spectral measures I will talk about are unique, regardless of the type of extension you take. So they're sort of canonical to the dynamics of the Koopman operator. So this is the picture. So here's the disk in the complex plane, and for this talk, the spectrum is going to be a subset of this disk, of this circle, sorry. And on the circle, there's going to be some measures that we're trying to approximate. Okay, so for those of you with a background in numerical analysis, a lot of what we're going to talk about sort of has motivation from geometric numerical integration, where you're trying to build methods that preserve key geometric features of, in this case, ordinary differential equations. So to start off with, what we're going to want are approximations of the Koopman operator that satisfy this isometry property. Okay, and that typically doesn't happen with EDMD, and this will allow us to get stability, better long-term behavior. Okay, any questions on this setup? No? All right. So let's go back to my favorite example, the shift operator. So remember, we had this 2A infinite matrix, which is unitary. But then when we truncate, we get a Jordan block. And remember, lots of Koopman operators are built up out of this. So this is a measure, you can think of this as the Koopman operator of a measure preserving system, a shift system, right? So does anyone have any idea how you might take this Jordan block and fix it in a very simple manner to get something that's a bit like a shift? Anyone?
The one on the bottom.
Yes. Have you seen this before? Okay. So you turn it into a circular matrix, okay, and then it becomes unitary. The spectrum is actually Fourier modes along the circle. So this is related to the fast Fourier transform as well. The spectrum is stable, and as you increase n, these eigenvalues will fill up the unit circle. So what we're going to do first of all is we're going to try and do this picture for general Koopman operators. So for this particular matrix, there's a lot of structure. You can kind of spot what the answer is, but it turns out that the underlying step here is actually related to a polar decomposition of this matrix. Okay, so you can take any finite matrix that has a polar decomposition, just like a complex number does. Okay, so to do this, I'm going to show you a different interpretation of extended dynamic mode decomposition. So last lecture, remember we said that it was a Galerkin method. Equivalently, you can think of it as a least squares problem. And this is the key to realizing how we might generalize this to get a picture a bit like this. So remember, we have this dictionary, psi1 up to psi n. These are our basis functions. Okay, and Then if I have an observable G inside this span of this dictionary, I can represent it in terms of what I call quasi-matrix. So a matrix whose columns are functions times this vector, okay, of coefficients. And what I want to do is I want my Koopman approximation matrix on this coefficient space to be a good approximation of the true Koopman operator. Okay, so EDMD, what it's doing is you take this least squares problem, okay, so you take the maximum of the squared residual over your coefficients, okay, which you can rewrite like this. And because you don't have access to this integral directly, you approximate it using quadrature, and this leads you to a weighted least squares problem, which equivalently gives you the EDMD matrix. So this is just another viewpoint of this Galerkin method, which is a bit easier to generalize to restrictions. So remember, in one of Steve's talks, he was talking about physics-informed DMD, where you take DMD and you add constraints. So we're going to do that in EDMD. It's a lot harder to do it in EDMD than DMD, because DMD is, remember, posed in state space. Okay, so it's much easier to do things like, okay, how do I enforce causality, stuff like that. Whereas if you try and do that in coefficient space, it's a mess. Okay, so this is one of the only examples I know where you can actually get somewhere. One of the things we're stuck on at the moment is how to do constrained EDMD in other situations. So if you have any ideas on that, please talk to me. Okay, so we have this least squares problem. So here's the simple alteration. Remember, we had this approximation of this Gram matrix, or this inner product between the basis vectors. And measure preserving means, well, what does it mean? So if I take my vector of coefficients, this is going to be approximately equal to the norm G squared. We're in isometry, so this is the same thing as the norm of kg squared, which is the same thing as this. We want this to hold for all possible choices of G. So we're going to enforce that this matrix here is equal to this matrix. Okay. You apply quadrature in the same way, you get the same, almost the same. You just go back and compare. Yes. So notice there's an extra G inverse here, inverse of the square root, just to account for the change of basis. And then you have this constraint here. Okay, so you've gone from an unconstrained least squares to a constrained least squares. This is actually known as an orthogonal preclusive problem, and you can write down the solution in terms of the SVD. Okay, that's it. So this gives you this algorithm. Very simple, almost as simple as EDMD. So you take your snapshot data, your quadrature weights, your dictionary, you compute these matrices as before. You do a QR decomposition. So I should thank Zlatko DreamHack for this trick here, which makes it a bit more stable than doing just the blind SVD. And then you do an SVD of this thing. It's just linear algebra. You get the eigendecomposition of a unitary matrix. Okay, so you're working out a unitary matrix with respect to your G in a product. That's what's going on behind the scenes. And then you can go back to your original coordinates and you do the same for your eigenvectors. Okay, right. So for the notation in what follows, Vn will be the span of these basis functions, and Pvn will be the orthogonal projection from the L2 space to this Vn. There's another interpretation, which I'm probably not going to have time to go into, which is as you collect more and more data, and remember we're assuming that that means the G matrix and the A matrix of EDMD converge. This is actually equivalent to a polar, sorry, the unitary part of a polar decomposition of this compression. Okay, so you're taking the Galerkin approximation that EDMD spits out, and you're taking the nearest possible unitary approximation.
What's polar decomposition, man?
So you can represent any matrix as a product of a unitary matrix and a positive Salvatore matrix. And then you throw away the Salvatore part. And you can see that using the SVD as tricks to get it. Equivalently, it's the closest, well, it's a closest unitary matrix with respect to either the Frobenius or Thunel. All good?
I mean, I guess it's the positive, I guess, is the polar of, do you get this, yeah, I guess, do you get the same unitary matrix
You don't always get the same unitary. It's not necessarily unique. So here, you can place 1 by any z of modulus 1.
Is that generic that you get non-unique?
Yeah, so it depends whether some of the singular values are equal or not. But that doesn't really matter in the convergence analysis that follows. You're basically doing a closure of your projection to subspace to get a unitary approximation. So this picture is really nice because you're sort of wrapping back into the space. That's exactly what the polar decomposition is doing. You're getting rid of the positive self-adjoint part that sort of stretches it and does other stuff. Yeah.
So if you multiply this by some z on the unit circle, like e to the I alpha or something, then under iteration, does that mean that you're adding an additional rotation of alpha per iterate?
What do you mean?
Well, I mean, it's like
so rather than dissipating.
Yeah,
so
I'm thinking of like an eigenproblem. Like let's say you wrote the eigenproblem for this, where you stick in the this e to the I alpha.
Oh, here instead.
Yeah,
it would have the same spectrum, right? Just be a change of, I don't know, I can't do that in my head, but I wouldn't be surprised if you could change the basis to get the same spectrum.
It seems like every time you iterate, you have this additional e to the I alpha that you're rotating. So the eigenvalue should change by the phase.
That might contradict the convergence theory I'm about to present. So I expect that might not be true, but I don't know without seeing down on the paper.
I think it's okay because I think what you get is you get points around the unit circle with a spacing of order 1 over n.
Right, and
And if you shift them by an alpha over n, who cares? When n's large, you're still approximating the unit circle.
Yeah,
I guess, but if you want to interpret an iterate of the operator as something dynamic, then you're adding this additional rotation.
But I think it's e to the I. It's an alpha over n rotation, so it's a small.
right, but if n is really, really big and you're thinking about a fixed vector inside L2, its coefficients are going to decay, so you're going to get a very small contribution.
Then I'm confused about your comment that it's non-unique up to multiplication by.
Up to this phase here that you can add. But this is only affecting the tail of the expansion, right? So as you increase n, it's not going to, which is exactly the kind of thing Marco's saying.
So this arbitrary phase goes to 0. So
it's caught in the tail of the observable, so it doesn't make a difference.
So the large n limit, the phase changes, the uniqueness is shrinking to.
Well, for this particular example, I don't know whether it's complementary, but you'll see in a second what the convergence theory is. Okay. Right. Okay, so I'm now going to talk about convergence, which will hopefully help with this question. To do that, I'm going to talk about spectral measures. So my apologies if you've not seen a spectral measure. Hopefully, through comparing to the finite dimensional case, you'll get the intuition. So if you take a unitary matrix, finite matrix B, it has an orthonormal basis of eigenvectors Vj. So you can write diagonalization in terms of projections, which is how I like to think about it. So you have these Vj, okay? Vj star, this is an orthogonal projection onto the span of Vj, okay? And this sum here is just the identity matrix or operator. Okay, so any V inside your Hilbert space, in this case Cn, can be represented like this. Now, when you represent it like this, it's very easy to apply B, okay, because you know how it acts on eigenvectors, right? You just get multiplication by lambda j. Okay, so this is just a way of thinking about diagonalization. Now, when we go to infinite dimensions, unitary Kuban operators, often, particularly for chaotic systems, there's no basis of eigenvectors. In fact, there might not be any eigenvectors at all. Okay, so what we're going to do is we're going to replace this sum of projections by an integral over something called a projection valued spectral measure. Sounds super scary, but all it is it's a probability measure, which instead of spitting out a number, spits out a projection. Okay, you can kind of think of projections like numbers. You can add them, you can do all sorts, well, you can compose them and do all sorts of stuff. Okay, so when you get this, you can represent your observable in terms of this integral with a 1. Okay, and then kg, you replace lambda j by lambda. And this goes back to, I think it was von Neumann who wrote this down first. I might be wrong, but he was looking at this kind of stuff for quantum mechanics. Okay, so you trade this sort of discrete sum for a measure. The measure might have atoms, which would correspond to eigenvalues, or it might have a continuous part. Okay, so we're going to try and compute these components and understand what they mean physically for Coulomb operators. Okay, so you have these projection value measures. You can get them back to probability measures by taking inner products. Okay, so this projection, so for any open set U, okay, of the circle, mu G U, so this is a number. So you take the projection associated with U, you act with G in a product. G, if G has not 1, this is a probability measure. Okay, so mu G takes a set U, spits out a number, just like you do when we have a probability measure over a real line. Okay, everybody with me so far?
So you're now restricting to bijections, right? So
I'm always assuming, you can assume for the sake of this talk that Coulomb operator is unitary, but everything I'm talking about you can apply to the unitary extension of an isometry. And these measures are unique, independent of
just a small comment
Yeah.
on the question. There is a larger theory on Banach spaces that goes back to Dunford and Schwartz. I wrote it up for a pretty large class of Coulomb operators on Banach spaces that extends this, but for unitary, it's exactly the same.
Dunford and Schwartz Part 3 is the mega book on all of this stuff. It's I've got it in my office, but I've never dared to read it.
Actually, Dunford's review paper is a fantastic read. If you don't, the books are. And the operator theorist, like me, Putina tells me that it was forgotten, which is really interesting.
Do you have a question, Gary?
Yeah, just if you like, is there some sort of intuition for this?
That's the next slide. That's the next, exactly. So these are measures on the unit circle. What do they mean physically for Coulomb? Well, so the probability measures on this, right? You can look at their Fourier coefficients. Okay, these by a change of variables are just equal to this integral here. So these are moments of the measure. Okay, and you unwind what they mean in terms of the Coulomb operator, and you get these correlations. Okay, so the Fourier coefficients, sorry, of these measures are correlations. Okay, so that's the connection. So they characterize four-time dynamics, and in fact, we'll see that they can give the Coulomb motion position.
So I should take the Fourier transform of the correlations in order to understand.
So the Fourier coefficients of the measure are the correlations.
Yeah, but the measure itself, the best intuition is I take the Fourier transform of the correlations.
You sum up, well, yeah, okay. Sure, okay. Yeah. Okay. So what does MPEDMD do? Well, you can take your discrete approximation of this measure, which is just written like this to take into account the different bases, and you can study its convergence in the weak sense. Okay, so this is captured by something called the Wasserstein metric. So what does this mean? This means that if you take any Lipschitz function over the circle, okay, and you integrate it against the difference between these two measures, this is small, then this means this integrals. Okay. So this means that if mu g and m converges to mu g inside this metric, the integral against any function like this will converge. And in fact, there's a uniform upper bound of the error. Okay, so here's the theorem. Suppose your quadrature rule converges and your basis, or your subspace rather, satisfies this density property. Then for any fixed g, so this is related to your comment about the tail, and gn, so these are the coefficients so that your approximations inside your subspace converge to g as you increase the size of the subspace here. Then, if you take the lim sup as m goes to infinity, so more and more data of this Wasserstein distance between the measure we want and this guy, and then you take n to infinity afterwards, you get 0. Yeah. So your measures converge in the weak sense. Also, what's really nice is the only example I know of this. So please correct me if you know of another example, because I'd be very interested. If, for example, you take as your basis g, kg, k to the n minus 1g, so this is a Krylov subspace, or for those of you who've used delay embedding, it's exactly delay embedding, then you actually get a rate. Okay, so you can bound this by some constant times log n over n. And this comes through taking the Fourier expansion of Lipschitz function and matching moments. Okay, the moments correspond to powers of k.
What's the old G?
Well, g is just my expansion. So in fact, it's any vector, right? It's any vector, gn, that satisfies this. So I'm thinking of these as approximations inside my subspace of G.
And the signs are your, say,
Besides my quasi-matrix. So remember, EDMD has this quasi-matrix. So I can represent a G inside my subspace like this, but of course the G inside the theorem could be an arbitrary G. Okay. Now, think about what happens if you take EDMD of the two-way shift. You're going to get a Jordan block whose spectrum is just 0. So there's no hope that the spectral measures can converge, right? So to get this theorem, you really need the unitary approximation. And the reason you need that, there's another reason. If you want to prove this theorem by taking a truncated Fourier series of the Lipschitz function here, you'll get a tail, and you need to uniformly bound the action of the truncated operator on that tail. Okay? So you need a stable approximation. Okay? Whereas if you have those Jordan blocks, it's not. Okay. So you can prove the projection value measures converge, the Kuban mode decomposition spectrum, generalized eigenfunctions. We're going to get to that. So I'm not going to dwell on that now. But the key ingredient is unitary discretization. So that's all very abstract. Let me show you this in practice. So here's the Lorentz system. And again, I'm going to solve this with a multiple time stepping method to get a hopefully accurate approximation. Of course, it's chaotic, so I have to rely on things like shadowing. But the time step will be 0.1. And then my G, so this is my observable, will be this particular function here, just chosen to have an interesting spectral measure. Okay, C here is a normalization constant, so that this has norm 1 with respect to the physical measure on the attractor. Vn, my subspace or my dictionary, will just be the span of these base elements. So I'm applying delay embedding. And to visualize the spectral measure, I'm going to look at the cumulative distribution function, which is this function here. Okay, so theta is giving you the angle along the circle. This is your cumulative distribution function with 50 basis functions with 500. Okay, and you can see it converging to a distribution. And in fact, you can even measure the error in the Wasserstein metric. And of course, I don't know what mu g is, so I've just taken a much larger n to compute this. And you appear to get this 1 over n convergence rate as the theorem predicts. Okay, so it's actually pretty cool, right? That even with just 1,000 basis functions, you can get 3 digits of accuracy for this Wasserstein. Yes?
What's a quick question? Is there any assumption on the underlying system for the rate of convergence?
No.
So
Now, I think I know what you're going to. So it's convergence in n, not m. Yes.
in the dictionary, right?
Yes.
Because you know what I'm going to ask you.
Exactly.
The periodic approximation theory tells you that the underlying system. Okay.
Yeah. So this convergence is after you've taken this.
Okay. I missed that. Sorry.
And we're going to see in the third talk that it's really hard to get. In fact, it's impossible to often find a convergence rate in M. So that's where we're going to go a bit crazy with that.
First, depends strongly on the underlying system.
Okay. Here's an example showing why you want to preserve a unitary approximation. So this is from some real-world turbulent data. Okay, so you have a jet, a plate, and this is like a window that I'm going to observe. What I'm going to do is, so I take the velocity measurements at points. The ambient dimension is about 100,000. And I'm going to compare the measure preserving EDMD approximation to the pi DMD. So that's the corresponding guy in for dynamic mode decomposition. The point here is that pi DMD is not preserving the correct metric G. Okay, so remember we had to be careful about the measure that we're preserving, and EDMD. Okay, and I'm looking at the mean turbulent kinetic energy of forecasts. Okay, so unseen data, forecasts of unseen data at different y. So y is the height of the plate. So you have an inhomogeneous flow because of this plate. So you get different statistics, different heights above the plate. Here's 5 millimeters above the plate. The green is what MPEDMD is getting. The black is what you want, nails it. The blue is stable, but gets the wrong measure. Okay, and EDMD is unstable because you have an eigenvalue outside the disk for this example. Okay, and you can do the same thing at different heights. And then you can actually plot this kinetic energy against height to try and see whether you're capturing the statistics. And you are, right? So whereas pi DMD is stable, but not capturing the statistics. So the point I'm trying to make is that if you go back to this problem here, dealing with the correct G, okay, so properly thinking about EDMD as a good outcome method is crucial if you want to get a physically good unitary approximation. You can't just apply stuff in POD world. Okay, you have to be a bit more careful. Okay, and then we can look at the flow as well. So what I'm going to show you is a video of the predictions. So this is the flow, MPEDMD, pi DMD, EDMD. These are the wave number spectra. So these are giving you sort of like spectral measures at different frequency scales. So you can think of them as a fingerprint of the turbulent statistics. So you see that pi DMD is, it's stable, but it's not getting the right kind of behavior. This is going to blow up, right? So plotted them on the same color scale. So hopefully in not too long, you'll see it starting to get unstable.
So what is pi DMD again?
Pi DMD is where you take DMD, and you enforce the DMD matrix to be unitary in POD basis. So whilst you're going to be stable for a fixed discretization size, not necessarily for all discretizations as you increase that, you're preserving the wrong inner product. You're unitary with respect to the wrong inner product. Okay, so you can see if you don't preserve the key symmetries or physical properties of the flow, you're going to get wrong stuff.
Where the flow itself.
Where the flow what? That's this. This is the flow. This is the velocity.
Like the left one. Like the left one is the truth, right?
Yeah.
At least when I was looking at the stationary.
Okay. Let me start again.
I know.
So it goes up to a time point because that's all the data I have.
Oh.
And then this is like going for much longer. Yeah. Okay.
How many dimensions in MP?
Size of the basis?
Yeah.
Oh, good question. It's years since I've remembered that. The paper will say maybe 1,000, something like that. It's not very big.
Okay, so 3-4 orders of magnitude less than.
Oh yeah. So this is 100,000. Yeah, and then you got velocity as well. So, yeah. And I should also say at this point, before we launch the generalized eigenfunctions, that there is a lot of work in the unitary Koopman case on these types of approximations that preserve measures. So if you have systems where you could do periodic approximations, so Igor has some very nice papers on this, then you can also get similar conservation of the measure of the isometry property, and also extra properties such as preserving the multiplicative structure of the Koopman. So there's a whole load of papers that sort of try and force this unitary approximation for measure preserving systems.
Yeah, but this is the right thing to do for large dimensional systems.
Yeah, I'm not sure how you do it.
We did work for low dimensional systems.
Okay, so let's go back to the shifts. So, I always love going back to this example. Okay, so I had this mysterious thing in the first lecture where I said it had no eigenvectors, right? So let's actually try and show that. So suppose that we want to solve for a fixed z, this equation here, okay, this eigenvector equation. So Ej is my canonical basis of L2z. Okay, so the shift just takes EJ and maps it to EJ minus 1. And I'm going to expand my candidate eigenvector in terms of this basis. What happens? Well, if I solve this equation, I'm going to get powers of z to the j. This doesn't live in L2z. For example, if mod z is less than 1, this blows up as you take j to minus infinity. If mod z is greater than 1, it blows up as you take j to infinity. If mod z is equal to 1, okay, it doesn't decay, so it can't converge in the L2 sense. Okay, so how do you get around this problem of not having an eigenvector of this unitary operator? What you can do is you can apply test functions or test vectors. Sorry, I'm probably going to interchange vectors and functions, but I hope you forgive me. So, for example, let's take mod z equal to 1. Let's take a candidate vector phi, okay, phi j, where the phi j decay faster than any inverse polynomial. Okay, so you have some very strong regularity on this phi. If we take the inner product of u, z, and phi, we can kind of make sense of this by taking an appropriate limit as this sum here. Okay, so these phi j are regularizing this, this non-convergent series. Okay, what does that mean? So if I sort of imagine that I can apply the usual rules of linear algebra and take u, my unitary operator, so that's this two-way shift, apply it to uz, I can apply the adjoint to phi. What I'm going to get back is this equation here. Now, if I compare this sum to this sum, this is equal to z of the inner product here. So you can think of this thing here as satisfying the eigenvector equation, eigenvalue equation, in a distributional sense when you apply it to these test functions. Okay? And you can do exactly the same thing for Koopman operators that don't have eigenvalues. So they have a continuous spectrum, and there's a nice Koopman mode interpretation of these distributions. Okay, so that's what we're going to try and get next. Okay, so these are called generalized eigenfunctions, not to be confused with the generalized eigenfunctions that Igor was talking about to do with algebraic multiplicities, and generalized eigenvalues, which just correspond to the spectrum. Okay. Everybody okay? Right, do shout out if something's not clear. So, this is called a rigged Hilbert space. If you want to find out more about this beautiful subject, read the books of Gelfand. Okay, so let's look at the nonlinear pendulum as an example. So Steve had this very nice paper that he was talking about the other day, where he's saying, okay, the pendulum is a very tricky thing to apply DMV to because it's got continuous spectrum. We're now going to work out what those generalized eigenfunctions look like for the pendulum. Okay, so let me keep track of things. Yeah, so my state space is just angle times I guess you call it momentum. I'm not a physicist, so x2, right? So x1 and x2 live inside this space. I'm going to solve this system, okay, with a time step 1 and collect data, okay? And I'm going to look at the Lebesgue measure on this space here. So it's a Hamiltonian system. It preserves this measure. Okay, so what I can do is I can actually take this system, which is integrable, and I can look at it in action angle coordinates. Okay. So suppose that you can take the system and write it down like this. Okay, so you have I dot is equal to 0, theta dot is equal to I. Okay, now I'm generalizing this picture here to n dimensions. So you can do this for the pendulum with n equals 1. It turns out that what you can do is you can take your test functions, okay, so G inside a Schwartz space, okay, so it's written down in terms of Fourier coefficients, okay, in terms of I, and then you've got these angle parameters here. Okay, so you've got your Fourier transforming in the action variable, and then you're looking at these angles here. And then you can represent this coefficient here in terms of this sum. Okay. And what you get back is a decomposition of G, Okay, so G is this sum here, these coefficients of this here. So you take this block and you shove it in here. And these distributions here can be written down as, sorry, it's hard for me to pass the slide. So you've got what you've got. You've got a delta function, delta distribution supported on a hyperplane. Okay, so theta, which shouldn't be confused with the angle coordinate, lives inside this space here. Okay, and then you've got an orthonormal basis along this hyperplane. So this is generalizing what was done for the pendulum in 1 dimension by Igor to 10 dimensions. So let me actually.
So I was going to ask where the end came in, but this is not the pendulum.
This is a generalization of the pendulum. So I'm saying, for example, you could take the pendulum, which can be represented in actual angle coordinates in 1 dimension, but let's do the general dimension. So you can write out any G. What I'm getting at is you can write any observable G inside a Schwartz space in terms of a sum, an integral of an inner product of G with these generalized eigenfunctions, which are distributions that correspond to delta distributions along hyperplanes associated with the action variable, and then you've got this orthonormal basis over the angle variable.
And where's the radon transform?
So the radon transform is how you deduce this step here. Let me pass that. So you've got Fourier here, and if you want to, because you're integrating over a hyperplane, right? So that's, yeah. It's a horribly unclear slide. I should have cleared this up a bit better, but you can find this in the paper for the actual paper. Okay, so this will hopefully be a little bit clearer. So let's go back to our picture. We had before, okay, finite matrix, you have this expansion. So now we're replacing spectral measures by these generalized eigenfunctions. So you can take a G, okay, you can integrate over the spectrum, inner product with these distributions, okay, and then the Koopman operator, you get e to the I theta due to a change of variables times this thing here. So if we go back to the Koopman mode decomposition, eigenfunctions, eigenvalues, Koopman modes. Okay, so the distributions acting on your observable, you think of them as coefficients in the expansion. They're the Koopman modes.
Sorry, what is the measure here? The new?
What, sorry? Oh, so that's a non-constructive measure. You can recover it from the spectral measures, but there is a measure that satisfies this. It will depend on the system. So if we go back here, right, you package this all in, you're going to get a particular measure. Okay. In fact, let me skip ahead to the picture for the pendulum, because I think this is a bit easier to see. So these are the generalized eigenfunctions as I shoot along the continuous spectrum. So this is the spectral measure, and you see that they're supported on these hyperplanes, and then you get these harmonics over the hyperplanes. Okay, so I've decomposed the pendulum into eigenfunctions of the Koopman operator that look like this. Okay, so I've got a continuous variation. Okay. I've probably lost everybody by now, but I hope it's visually clear. Okay, so
Just to Julia's question, it's the Fourier transform. The new is the Fourier transform of K and G in a product with G. So you take the time series of K and G in a product with G, do a Fourier transform, and that's, you know,
okay,
So it's the measure
the measure of the correlation signal.
so what I wanted to sort of end with was how we actually compute these. Okay, so I've got a very particular formula here where you've got a lot of structure, right? An integrable system. Often you don't have that. How do we actually compute this? So what we're going to do is use something called the Carathéodory function, which is a beautiful object. So you take the Koopman operator, you shift by some z, not on the unit circle, k plus zi, and then you take the inverse of k minus zi, and you apply it to G. You can use if you take this expansion here, you're thinking of this as a scalar, right? The Koopman operator is a scalar. This is a rational function. You get this times this. Okay, and now it just becomes harmonic analysis. Okay, so if I take r, so this is my radius outside of the unit disk, so 1 plus epsilon, and some angle where I want to compute this generalized eigenfunction, right? So remember, I've got an integral over the whole spectrum. So I've picked an angle at which I want to probe this generalized eigenfunction. What I can do is there's a trick, so I can take this evaluated r minus 1 e to the I theta minus this evaluated r e to the I theta, 1 over 4 pi. You run through the algebra, and you get back this beautiful thing times this. Now, does anyone recognize this function?
Also kernel.
Yes, yeah, fantastic. Okay, this is the Poisson kernel. Okay, so this is a smoothing operator. So I take this thing, and I can think of it as a smoothed approximation of my generalized eigenfunction. Even more so, this thing can be represented in terms of these. And these I can approximate with DMD methods. So I have a link between DMD methods, Galerkin approximation, and a smoothed approximation of this crazy generalized eigenfunction. Okay, so that's what this kernel looks like. So as you decrease epsilon, so epsilon is the smoothing parameter, you shrink r, so you're sort of evaluating here and subtracting your pinching, okay? As this sort of, as epsilon decreases, this kernel gets bigger and bigger and sharply localizes around 0, and you recover the generalized eigenfunction in a precise sense. So then you can get convergence of various topologies. Now, we can represent this in terms of this function here. So now we've got to work out how to get a data-driven approximation of this product here. To do that, we need to solve the inverse of k minus zi, right? So we need the resolvent. Now the problem, if I take EDMD and I compute this inverse for z inside the disk, okay, you can show, it's very easy, that you're going to get something that blows up exponentially. So this is another reason you want unitary approximations, because if you change from EDMD to MP-EDMD, you can show that this inverse exists. You can show that the inverse of the MP-EDMD approximates this inverse as you increase the size of the dictionary. So all you do for rigged DMD is you shove in the NP-EDMD approximation of this resolvent. Okay, you can show it converges. And so you get a 3-limit approximation. You take data to infinity, n to infinity to get this. And then you need to go here and take the smoothing to 0 to get the generalized eigenfunction. So with 3 successive limits, okay, you can get the generalized eigenfunction. Okay, so that's not quite the end of the story. The Poisson kernel is a rubbish kernel, dare I say it. The reason is it converges slowly at order 1 rate. So if you look at the convergence rate of these approximations applied to, for example, test functions, you get a very slow order 1 convergence up to some logarithm. What you can do is there's some very nice tricks to construct rational high-order kernels using this Carat-Theodori functions. There's some nice symmetries. So these are what the kernels look like, okay, for different epsilons. Notice that they're not necessarily positive. Okay, there's a misconception in harmonic analysis often that you need positive kernels for things. No, you don't. Okay.
Are these named like for low end? Names?
No, we just made them. I don't know what you call them. Yeah, I didn't want to attach a name in case there's a name. I don't think so. So you get this. Okay, so suppose your quadrature rule converges, you get this density assumption again. Okay, there's a way of choosing often your n depending on your smoothing parameter. It's a bit heuristic, but what you get is this fast order n convergence for generalized eigenfunctions in the topology of the test space. Spectral measures as well, various sets of pointwise LP, and also forecasting. Okay, so you get these smoothed approximations. So let's look at the big picture. What have we got? So here's how you do it. So you have, for example, this Lorentz system. Okay, you get data, you form the unitary Koopman approximation. You then do this pinching trick, and that will give you these spectral measures. Okay, and also these generalized eigenfunctions. And now you can see the picture that I showed at the start. This is a smooth approximation of this generalized eigenfunction. Okay. Any questions? No. Okay, so let's look at some examples. Let's look at the cat map first of all. It's a beautiful, beautiful map. So yeah, it kills this cat. Loves it up and moves it all about. There's a very nice video of this on Wikipedia. So what is the state space? It's this this torus, okay, and then the map is just this polynomial mod 2 pi, okay. And what we can do is we can take, for example, this G. Okay, so this is just chosen to have a nice spectral, interesting spectral measure, and I can apply delay embedding, so Krylov subspace with 500 basis functions. And I'm using for my quadrature 50 by 50 quadrature rule on the torus, right? So you can use a trapezoidal rule to get exponential conversions. This is the spectral measure, okay? The true spectral measure that you can work out analytically because of the structure of this this map. And here's the convergence for different orders of your smoothing kernel. So this is the maximum error of my smoothed approximation of this measure. So I'm thinking of approximating the density, the Radon-Nikodym derivative. Okay, so you see that you can get away with larger kernels, you can get away with larger epsilon. And that's really important because as epsilon shrinks to the disk, it becomes more expensive to evaluate the result. You need a larger number of larger size of a dictionary, so you need more data. So you're going to save a lot of data. You're going to be able to get away with much less data with much larger epsilon. Okay, so that's why this smoothing is really useful. And you can do the same thing with the generalized eigenfunction in the topology of test functions. And this is what they look like. So remember, they're not converging to a function, they're converging to a distribution. So let me read this. So you've got the order of the kernel in the columns, and then you've got the smoothing parameter. So you get a better approximation the further that way you move, and the further that way you move. Okay, so you see that you're getting to something very, very oscillatory, right? So it does have a limit in a distributional sense, but not in an L2 sense. So you can think of this as a Koopman eigenfunction of the cat map. We've already seen the pendulum.
I want to ask about that, but also I want to ask about the previous slide.
Yeah.
Quickly. So, so you choose. Is there an obvious connection between the G that you choose and the generalized eigenfunction?
Oh yeah. So what I'm actually so the generalized eigenfunctions are unique, but what I'm actually computing, which I perhaps was a little bit unclear about, is I'm computing G, but also with this coefficient in front of it, where I'm taking the inner product. So sorry, G theta, which is the eigenfunction, and then the inner product of G theta with G. So there are ways to recover G theta with some post-processing tricks. But for the pictures I'm showing you, there's also this coefficient in front of it as well. So I'm computing the projection of my chosen G onto the eigenspace of the generalized eigenfunction.
And then for the pendulum,
yeah,
I noticed the peak. So I guess this is a function of the choice of G that
yes.
chose.
If I chose something orthogonal to the atom here, you would see the peak.
I mean, at the peak, it seems to be filled in. The I is filled in.
Yes.
And I'm just curious, like why the I filled in?
Yeah.
So of the I, but I guess it's
at theta equals 0. There are actually true eigenfunctions of the Koopman operator in L2 sets. In fact, there's a whole subspace of them corresponding to. If we go back to the action angle coordinate, right? So if I is equal to 0, right, you're going to get this orthonormal basis here.
So we're showing in the movie one.
Yeah. So this remember, this is the projection of my chosen G onto the subspace of generalized eigenfunctions associated with the spectral parameter.
Yes. The question is yes. The reason you see the inside of the I and not the complement is due to the G.
Yeah. Exactly. Yeah. Okay. So finally, I've not talked about how you get the rig structure, how you get the test functions. So for this particular cylinder, you can choose Schwartz functions for your test functions. how would you choose a suitable set of test functions on the Lorenz attractor, where you've got this sort of fractal attractor? Right? How would you pick the notion of Schwartz functions on such an attractor? Well, there's a trick. What you can do is you can do it in coefficient space rather than physical space. Okay, so here's the theorem. So suppose that your Koopman operator is represented by an infinite matrix with finitely many non-zero entries in each column. You can build S using weighted sequence spaces. And it's always possible to build such a Koopman representation using delay embedding. Okay? So if you take unions over different choices of G of these Krylov subspaces, there's a way of building your test function. So remember, G has to live inside your test function space. There's a way of building your G, building your test space from these unions of weighted spaces. Okay, so you can think of this as like Schwartz space, but in coefficient space with respect to Krylov subspaces. Okay, and that allows us to get generalized eigenfunctions of the Lorenz system. And here you go. So here's the spectral measure. Here are the generalized eigenfunctions. Okay, so I'm applying delay embedding. So I'm getting this Krylov subspace, and I'm choosing my G to live inside this weighted coefficient space. And this is what they look like. Yes.
How restrictive is this assumption that
This.
the top one, the top bullet point? Can I, like, what?
So you can always get it from delay embedding.
Okay. Oh, yes.
Now, there's no guarantee that this space will fill the whole Hilbert space, which is why I need to take unions of different G. But I always get an invariant subspace by doing this. If my Koopman operators. Well, okay, maybe I have to go backwards, but. Okay, I'll probably end with a couple more examples. This is a noisy cavity flow. So this is another example Steve was talking about, where I'm increasing the Reynolds number and the spectrum, the spectral measure is becoming smoother, right? So we think that as when you get to very large Reynolds number over here, that you get continuous spectrum. Okay, so Igor has a very nice paper where he's actually finding ways of measuring that. But what I want to get into is what do the generalized eigenfunctions look like? So for small Reynolds number, we're pretty sure you get periodic behavior with discrete spectrum. Sorry, point spectrum, I should be careful. And then probably mixed spectra over there. Okay, and this is what the generalized eigenfunctions look like. Okay, so this is a noise-free approximation. One of the nice things about having these high-order kernels is you can have a larger smoothing parameter and still get a good approximation. So it's pretty good at dealing even with noise, right? So it's pretty incredible that for a very high Reynolds number flow deep inside the continuous spectrum with lots of noise, you can still get a distribution associated with the continuous spectrum. Anyway, I was quite surprised.
So here are you've got many G, you've got lots of projections of different Gs, and
so the G
sum them all up here. Or, because
what
you
did we use?
right projection of
Yeah, no, you're right. I can't remember the G we chose. To be
but
honest,
it's just one G.
yes. No, sorry, not correct. What we were doing here was doing that post-processing to get. We were interested in not the. Yeah, sorry. We weren't interested in the eigenfunctions in this case, because remember, we're in a very high dimensional system, so it'd be impossible to visualize the eigenfunctions. We're interested in the Koopman modes, these coefficients, which you can do. So you have a whole family of G corresponding to each coordinate. You have a number here, and then you're plotting that number, and that's the Koopman mode. Just like you do for POD.
How do you get the image then?
So for each observable, so each coordinate, you have a coefficient, and then you just plot the coefficient, just like you do when you plot a Koopman mode using DMD. It's the same thing, but over the continuous spectrum. Yes, Igor.
Maybe a remark for Tony, because he gave a talk on this certain thing. When we computed eigenfunctions up to these beautiful pictures that Matt just showed of distributions, the pictures stay the same. I mean, the magnitude would change and the nature of the flow changed tremendously, but the underlying modes
Oh, across the Reynolds
almost
number?
didn't change.
Interesting.
And so if you take a look at that paper in physical review fluids, the nature of the modes didn't change. If you look at the proper orthogonal decomposition, the nature of the modes changes completely. But those Koopman modes and the Koopman distributional modes, whatever you want to call them in this regime, didn't change. So there is some tremendous robustness that I don't know how general it holds. It's an observation, but to my mind, it was very interesting. And the statistics in Tony's lecture yesterday showed kind of a smooth progression, you know, and they're composed of these modes. You can sum the modes up to get the statistics, right? I don't know, just
Yes.
kind of an observation.
So maybe I should end by saying if you're struggling to sort of parse all of the mathematics behind this picture, you should just think of this as like a Koopman mode that you get from DMD or EDMD, but with some tricks to make it robust over the continuous spectrum. Okay, so you're replacing that sum of modes by an integral of modes over the continuous spectrum. And this is one of the slices of that integral. Okay, so you have all of these modes for different parts of the spectrum, and you can, from those modes, recover the full action of the Koopman. Okay, so I will perhaps skip that and end with some pointers. So spectral measures and generalized eigenfunctions provide a diagonalization of Koopman operators for you for measure preserving systems, even when you have continuous spectrum. So standard DMD or EDMD methods don't preserve this unitarity or get the continuous spectrum. Okay? So you have to work a bit harder. So there's essentially two types of ways of approximating spectral measures. Okay, and this is much broader than the algorithms I'm talking about. This goes back to methods people use for Schrödinger operators, things like that. So MPEDMD applies this polar decomposition trick to get a unitary Koopman approximation. That gives you an approximation of a spectral measure in terms of Dirac's, right? So remember we had discrete atomistic things. So over here we had this, wherever it was. So remember we have this finite matrix, okay, and then we're getting this measure, okay, which is atomistic. The other way of getting stuff is to do smoothing. Okay, so we were doing this Carathéodory trick with this Poisson kernel, and we were getting, for example, you know, here you get a smoothed approximation of measure. Okay, and again, there are ways of doing that. People have done this for Schrödinger operators too. So there's kind of two flavors of approximating the continuous spectrum. Okay, so RigDMD not only does this smoothing, but it also does some tricks to get the generalized eigenfunctions. Okay, so those are the Koopman modes. So normally for general operators, you might only be interested in the measures, but here you're getting the full. Okay, so and sort of the story is that you can deal with continuous spectrum. You get convergence, you get rigorous theory, you get reduced effective noise. It's very robust. Yeah, and that's probably a good time to end the lecture and see if anybody has questions. Yeah.
I have a question about the convergence rate of the GetMap example.
Yes,
I think it was the very first example you showed before two slides back. Yeah, there was. Does it imply that now you should always take the highest order of m possible because the rates are better, or does it depend?
Within reason. There is some cancellation because what you're doing here is you're essentially summing up different Carathéodory functions. Beyond, I mean, I don't think you'd need beyond 6 or 10 in practice. If you took it very, very large, then you probably get some cancellation effect that might affect. Yeah. I always use m equals 6, because why not? And important thing that I should have said, to get this increased approximation, you need some smoothness assumptions on the measure, or if you're doing it in test function space on the test function. If you use higher order stuff, when you don't have those assumptions, you don't lose out. Okay, so it doesn't degrade the approximation. So if you don't know anything about the object you're trying to approximate, you might as well go high order because you'll still get as good a convergence as that order. Yes.
Just to confirm, so this algorithm, you run it once, you're supposed to get a curve that approximates the true continuous number?
So here, I'm picking a theta. Okay, so if I want the whole picture, I have to sweep over theta.
Okay.
That's actually a difference between the two flavors of approximating spectral measures. MPDMD, the discrete approximation, gets everything all at once. Smoothing, you always have to do it per point. So although smoothing is actually, you can show is a bit more robust, it's still a bit more expensive because you have to sweep over. But sometimes you might only be interested in a particular point of the spectrum. So it's local and a global. It's two sort of flavors. Yeah. Also, it's actually very efficient because what you can do is you can diagonalize in the MPEDMD eigenspace, and then for each theta, you're just multiplying by a diagonal matrix. So although I'm sort of pessimistically saying you have to sweep, it's actually very efficient in practice. Yeah.
Maybe just a comment rather than a question.
Yeah.
Maybe a challenge. As you have shown, there's very beautiful connections between classical harmonic analysis and unitary operators. And this is taking it kind of to a really nice another level. When one adds dissipation and you're now in the unit disk instead of a unit circle, that theory is missing. So there is something that's called generalized Laplace analysis that we have done over the years that provides a little bit of that as to how you can compute at least eigenfunctions using pretty much an equivalent of harmonic analysis. I've shown it in context of averages where you have a weight that's e to the lambda t, right? Instead of e to the I omega minus I omega t, you have e to the lambda t. But developing that would be actually extremely useful in general for operator theory. So if anybody has ideas, so this is a fantastic thing to work on because you're going to get equivalent results to what Matt just showed for dissipative systems.
It connects with what Gary was talking about. So when you look at the convergence analysis of that, you can essentially get stuff outside the essential spectral radius. Yeah. So there might be ways of doing that stuff for transfer operators too.
So, but the theory of polynomials on the unit disk, complex polynomials on the unit disk, is not developed in the sense that the theory of polynomials on the unit circle classically, right?
Right, because there are lots of nice connections between this object and orthogonal on the set.
That's exactly what I'm saying. So you don't have an equivalent theory on the unit disk, and this is a bit of an issue. So if anybody develops it, it's going to be a fantastic thing. Or if you have an idea, talk to me because I have some ideas.
Any other questions? Okay, maybe I should say what we're going to do next time, and then wrap up properly. So, where were we? We're going to look at adversarial dynamical systems. So we're going to prove what you can't do for Copenhagen operators, which I don't know, I find that quite fun. Maybe I'm a party pooper. And this will lead us to something called the SCI hierarchy, which allows us to classify this. And we're going to move beyond L2 spaces to reproducing kernel Hilbert spaces. Okay?